Human-Machine Interface, a tutorial, Part 1. HMI Design Philosophy. The design philosophy of the Human-Machine Interface, HMI, establishes the foundation for all subsequent configuration decisions related to distributed control systems, DCS. It provides essential guidance for designing an interface that promotes plant safety, efficiency, and usability. This philosophy must be realized through a collaborative effort involving operators, ergonomists, and multidisciplinary engineering teams. Central to this approach is the understanding that operator tasks across all process conditions drive display structure, alarm behavior, and control mechanisms. Task analysis, supported by ergonomic input, is mandatory to develop an effective interface. A dual-mode operating philosophy underpins the HMI design: awareness and exception. In awareness mode, the operator proactively supervises the plant, paging through displays, reviewing trends, and identifying deviations. The system must support this vigilance through a structured hierarchical display design and intuitive data grouping. In exception mode, the operator reacts to abnormal events. The HMI must immediately direct attention to relevant screens, prioritizing access to alarms, diagnostics, and corrective controls. Visual cues, alarm urgency, and automated prompts play a crucial role in guiding the operator through emergency or fault recovery procedures. The HMI must be functional across all plant states: steady state operation, upsets; planned transients, e.g., startups and shutdowns; and complete stoppage. The interface shall support task-specific displays that adapt to each condition. Operator workload, required reaction time, and display complexity vary with plant state. Thus, the HMI should dynamically match its visual and functional focus. Critical actions should be accompanied by automation aids or procedural guidance. And where actions are clear-cut and time-bound, semi-automatic or prompt-assisted execution may be configured. All monitoring and control interactions, whether from the ODS, IPS, tank gauging, or CCTV systems, shall be centralized within the DCS-based HMI. This integration abstracts the hardware origin of data, allowing operators to focus on actionable information rather than system boundaries. System health indicators for each subsystem must be visible to the operator, with warnings differentiated by severity and supported by intuitive prompts or instructions. Maintenance diagnostics may also be displayed if economically and functionally justified, though not at the expense of cluttering the primary operator view. The HMI must serve multiple user roles beyond the panel operator. These include shift supervisors, operations managers, and maintenance or technical support teams. Each group has distinct information needs, and the HMI must support them through role-specific displays and reporting tools. Operators require fast access to process data, control commands, and alarm guidance. Shift supervisors need performance summaries, alarm status overviews, and reports on control anomalies or sample delays. Support teams require displays for fault identification, maintenance status, and system configuration. Operators are the primary users, and their needs drive the overall structure. The HMI shall provide clear overview displays, intuitive control access, efficient alarm visualization, and tools for safe, economical plant operation. Shift handovers must be supported through summary displays and logs. These tools enable continuity, transparency, and efficiency across operational shifts. Additionally, reports should support tracking of operational issues, maintenance interventions, and production planning. Shift supervisors require higher-level graphical representations of plant performance, operational constraints, and yield versus target comparisons. Their HMI view must indicate alarm health, e.g., overridden, inhibited, or disabled alarms, and provide insight into controller modes. Displays must support prompt detection of irregularities, such as process losses to flare or slop, and allow quick access to laboratory sample tracking. A digital shift log should replace the traditional paper logbook and be integrated into the ODS for broader site access. Operations management relies on ODS-based displays to obtain a plant-wide view of operations. These views must be accessible via network PCs and tailored to highlight production, quality, and efficiency metrics. Support teams, including technologists and reliability engineers, use the DCS and ODS to access diagnostics, system alarms, and historical data. Minimum requirements for support users include displays for faulty inputs, tuning access, and configuration diagnostics, all within the system's security framework. In conclusion, the HMI design philosophy defines a comprehensive, operator-centric interface strategy that responds to every plant condition, user role, and operational requirement. By integrating ergonomic design, task analysis, and system-wide information access, it ensures that the control system enables safe, efficient, and intuitive plant management. This philosophy is not merely conceptual. It must be translated into actionable design decisions that shape every aspect of the HMI lifecycle. Human-Machine Interface HMI Tutorial Part 2. Users and their requirements. The Human-Machine Interface, HMI, including both Distributed Control System, DCS, and Operational Data Supervision, ODS elements, must accommodate the needs of a diverse group of users, each performing distinct roles within the plant's operation and support structure. These users include panel and field operators, shift supervisors, operations management, and support teams such as maintenance and technical personnel. The HMI configuration must be purpose-built for each user category, aligning with their task profiles and interaction patterns. This requires structured task analysis and collaboration with stakeholders to ensure the interface delivers relevant, actionable, and clearly presented information to all users. Operators, panel and field. Operators are the primary users of the HMI and demand displays that are fast, intuitive, and precise. The interface must provide real-time access to process conditions, alarms, and control functions. Each operator's workstation shall be configured with an overview display showing plant-wide status, active alarms, and key operating data. This overview acts as the gateway to detailed control displays. Operators must be able to drill down from overview to subunit or equipment-level displays with minimal commands, preferably in 3 or fewer steps. The operator's interface must support both proactive and reactive decision-making. It should include alarm-centric displays that immediately guide the user to corrective actions, as well as contextual process data visualizations that promote situational awareness. Additional capabilities, such as access to economic or environmental performance indicators, may be included to support optimized operation. Displays that facilitate effective shift handover are critical, providing concise logs, summaries of events, and relevant performance trends. Shift Supervisor. The shift supervisor requires a broader operational perspective and the ability to rapidly assess plant status, especially during shift transition. At shift start, the HMI must present pre-generated, condition-sensitive reports summarizing prior shift performance, key events, alarm histories, and alignment with production targets. These reports serve as a briefing tool, enabling informed supervisory decisions from the outset. Supervisory displays must include graphical summaries of process unit parameters, performance margins, and constraint windows. By visualizing the operating range left between current values and key safety, quality, or environmental limits, supervisors can assess opportunities for optimization or identify near-limit conditions that require intervention. Additional graphics should highlight overridden, disabled, or out-of-service alarms and indicate controllers operating in abnormal modes, e.g. manual or cascade bypassed. This functionality enables supervisors to trace deviations and initiate corrective or preventive actions promptly. Displays showing sample status, i.e., sampling time and lab results, help supervisors monitor analytical data availability and avoid decisions based on incomplete information. Loss tracking displays, such as flare flow, slop volume, or product losses, should also be configured. Finally, a digital shift logbook integrated into the ODS provides a centralized view of shift activities and enables seamless documentation and retrieval of operational events. Operations management. Operations managers need access to high-level overviews of plant performance, including efficiency, throughput, and compliance metrics. This group primarily uses ODS-based dashboards accessed through site-wide networked PCs. The data should be aggregated, contextualized, and presented in business-relevant terms, e.g., yield deviations, energy intensity, or emission summaries. The frequency of updates can be lower than for operator displays, but clarity, traceability, and reliability remain essential. ODS displays for operations management must enable both real-time monitoring and retrospective performance review. This supports strategic decision-making on plant-wide optimization, shift benchmarking, and long-term planning. Interfacing these displays with reporting tools further enhances their value for weekly meetings, audits, and regulatory reporting. Support teams, maintenance, engineering, technology. Support teams interact with the HMI for diagnostics, tuning, and system configuration. Their displays must present sufficient detail to identify equipment or instrumentation failures, understand the sequence of plant upsets, and evaluate control loop behavior. These users often require access to deep system views, such as raw data flags, bad input, out of service, controller performance indicators, and system configuration details. The DCS must provide dedicated displays or secure access zones for support users to manage maintenance tasks, modify tuning parameters, and retrieve historical trends or event logs. For example, a reliability engineer might access history files to investigate recurring shutdowns, while a technologist may review controller modes and feedback signals to assess stability. In some cases, access to configuration tools may be restricted to supervisory consoles operating in read-write mode with proper authorization. Where appropriate, support teams may also use the ODS platform for advanced analytics, integrating long-term trend analysis with external databases or CMMS, computerized maintenance management systems. The HMI must ensure that support users receive the necessary information without cluttering operational displays or disrupting the primary operator workflow. In summary, a well-designed HMI must satisfy the unique requirements of its entire user base. Operators need real-time responsiveness, clarity, and control support. Shift supervisors require high-level overviews and detailed status graphics. Operations management looks for performance insights and compliance indicators. Support teams depend on access to diagnostics, tuning, and maintenance data. By aligning interface design with these functional roles, the HMI becomes a shared operational asset, enhancing safety, reducing error rates, and enabling seamless coordination across the plant lifecycle. Human-Machine Interface, HMI Tutorial, Part Standard DCS Displays. Standard displays are foundational elements in most distributed control systems, DCS. Supplied by DCS manufacturers, they feature fixed layouts and default configurations designed for universal control and monitoring tasks. Although they are not custom-built, these displays offer quick access to essential functions such as instrument control, alarm tracking, and trend monitoring. Their integration into the HMI must align with the plant's operating philosophy and be tailored to support operator decision-making while complementing custom graphics. Before finalizing the interface structure, project teams should review the full range of available standard displays to determine how best to incorporate them into the overall display hierarchy. Their strengths lie in their uniformity, real-time responsiveness, and ease of use, while their limitations, such as rigid format or limited customization, must be balanced through thoughtful configuration and navigation planning. Control Group Display. The Control Group Display presents multiple instrument faceplates on one screen, each representing a control block, such as a pressure controller, valve, indicator, or switch. These faceplates provide real-time display and manipulation of key parameters like process value, PV, set point, SP, output, and control mode, auto, manual, cascade. Operators can view and adjust several related instruments from a single screen, significantly improving workflow efficiency during coordinated operations. Faceplates within a control group should be logically grouped by function or equipment, for instance, all controllers for a distillation column's overhead system. Typically, up to 8 faceplates can be shown per screen, depending on the system. Page numbers or user-assigned names are used for identification. Control group displays are best configured as support tools for graphic pages, allowing operators to access additional detail on demand. Trend group display. Trend displays visualize historical data from selected instruments over time, using multiple colored pens to differentiate each parameter. These trends help operators and engineers interpret process behavior, diagnose disturbances, and optimize performance. Each trend group is configured by assigning tag parameters to specific pens, logically grouped by process unit or system. Sampling intervals and retention periods vary based on the purpose of the trend. High-speed trends, 1 to 10 seconds, are used for critical variables like compressor pressures. Medium-speed trends, 1 to 5 minutes, are for general operational monitoring. Long-term trends, 5 to 10 minute sampling, stored for 30 days or more, support performance analysis and audits. Trend displays are a key resource during shift handovers, process upsets, and plant tuning exercises. Alarm summary display. The alarm summary lists all active process alarms in chronological order and shows their current status, whether active, acknowledged, or cleared. This display is the operator's primary interface for alarm management. It supports filtering by priority, alarm type, or plant area, and allows selective or individual alarm acknowledgement. To prevent operator desensitization or accidental silencing of critical conditions, total alarm acknowledgement functions must be disabled. This ensures that every alarm is seen and evaluated in context before being cleared. Tag detail display. Tag detail displays provide in-depth configuration information for a specific instrument, including tuning parameters, alarm thresholds, and internal logic. A mini real-time trend may also be included for tuning and diagnostics. These displays are primarily intended for use by engineers, technologists, and maintenance personnel. They are not typically used during routine plant operation, but are essential during commissioning, troubleshooting, or advanced diagnostics. Alarm overview display. The alarm overview shows a schematic representation of plant alarm states, often mimicking the layout of traditional hardwired annunciator panels. Each process area or functional zone is represented as a matrix cell that changes color when alarms occur. Color conventions, e.g., red for high priority, yellow for medium, visually guide operator attention. These boxes may act as navigational targets, linking directly to more detailed graphics, summaries, or control groups. Alarm overviews are especially helpful for supervisors, allowing them to assess plant-wide alarm activity and prioritize operator responses quickly. Summary. Standard DCS displays serve as essential operational tools, delivering structured, manufacturer-supported access to real-time data, control functions, and alarm conditions. While they are not customizable in the same way as graphic displays, their role in plant monitoring and safety response is critical. When configured correctly and harmonized with the broader HMI strategy, standard displays help reduce cognitive load, support decision-making, and ensure consistent performance across operational shifts. Human-Machine Interface, HMI Tutorial, Part 4. Graphic displays are custom-built, operator-facing visual representations of the plant process. Configured using the DCS graphic builder tools, these displays integrate static elements, e.g., vessels, piping, with dynamic data, e.g., process values, alarm states, equipment status, to form interactive schematics. They serve as the primary means for operators to visualize the process, navigate between systems, assess trends, and make decisions. While standard displays handle instrument-level detail, graphic displays provide the contextual understanding needed for efficient control and situational awareness. A structured, hierarchical design is essential to ensure consistency and usability. Operators must be able to form a mental map of the display architecture and navigate from high-level overviews to detailed equipment displays with minimal effort. The hierarchy generally consists of 5 levels: plant overview, unit overview, subunit, detailed process, and group tag level displays. Each level serves a specific purpose in supporting operations under steady state, transient, upset, and startup conditions. Overview displays. Overview graphics offer a high-level visualization of multiple units or entire areas. These displays are not cluttered with instrumentation or detailed control logic. They instead focus on presenting plant status, critical performance indicators, and dynamic summary values for key streams. Typically used in steady-state conditions, overview graphics help operators monitor the plant's general health and performance without needing to interpret fine detail. Within these schematics, clickable targets are configured to drill down into unit or subunit graphics. Tools like trend summaries, alarm status indicators, or production graphs may also be embedded. In fire and gas FGS area overviews, a simplified plot plan indicates the position and state of detection zones, with color-coded alerts and wind direction overlays for hazard interpretation. Unit displays. Unit displays represent the major process systems, e.g. crude distillation, hydrotreaters, and act as a bridge between overviews and detailed schematics. They present live data and short-duration trends for critical variables like feed rates, temperatures, product flows, and constraints. Used mainly during steady-state operation, unit displays allow the operator to monitor process stability and optimization targets. While they avoid showing instrument signal lines or tuning parameters, They enable fast assessment of process performance and alarm activity within the unit. Unit graphics also support quick transitions to subunit and detailed displays through embedded targets. Subunit displays. Subunit graphics break down major equipment systems, e.g., distillation towers, compressors, furnaces, into smaller process segments. These displays include equipment schematics with associated instrumentation, signal paths, and real-time values. They may show control loops, valve statuses, equipment interlocks, and include embedded trends for key parameters such as pressure, flow, or temperature. Subunit graphics are used for fine-grained monitoring and control and are particularly helpful during shift changes, troubleshooting, or minor transients. The level of detail is high but still task-oriented, only the information necessary to perform routine operations or respond to typical upsets is shown. Detailed process displays. Detailed displays offer a close-up view of specific process sections or equipment, such as a furnace coil system, compressor lubrication unit, or vessel control system. These schematics show instrumentation with complete control logic, signal lines, and all relevant parameters for tuning and adjustment. They support precise manipulation of set points, monitoring of manual overrides, and diagnosis of control behavior. Each instrument is represented with its tag, current value, and operational mode. Short-duration embedded trends help the operator understand variable behavior over time. These displays are particularly useful during tuning, commissioning, or restart operations where precise control and understanding of interdependencies are required. Multivariable control displays. These displays are dedicated to advanced control strategies such as modeled predictive control or multivariable constraint optimization. They include tuning parameters, process constraints, manipulated variables, and performance indicators. Used primarily by technologists or control engineers, these graphics provide a schematic interface to complex control logic and system behavior. Sequence displays. For batch processes or procedural operations, e.g., catalyst regeneration or product blending, sequence displays visualize each step in the control sequence and its current state. They often include active phase indicators, timers, and control interlocks. Operators are guided through automated or semi-automated processes with clear messages, visual cues, and embedded windows for alarms, messages, or help content. IPF logic status displays. These graphics represent the status of instrumented protective functions, IPFs, using logic diagrams or cause and effect matrices. They include override statuses, first failure alarms, reset commands, and diagnostics. These displays enable safe monitoring and reset of safety-critical functions and are often used by supervisors, technologists, and safety personnel during plant upsets or after trips. Transient-specific displays. Special graphic pages are created for transient conditions such as startup, shutdown, or major feed changes. These may be simplified or restructured versions of steady-state displays, focusing on sequence steps, interlocks, and key indicators relevant to the transient state. Embedded guide messages or windows may appear contextually to assist operators in managing these events. Other custom displays. Graphics may also be configured for supporting functions like recipe selection, product changeover, shift log entries, or maintenance status. While not tied to process schematics, these displays contribute to plant operation continuity and should follow the same interface conventions as the rest of the HMI. Summary. Graphic displays are the core visual medium for process understanding and decision-making. By organizing information in a hierarchical structure, from plant-wide overviews down to equipment-specific schematics, the interface allows operators to respond efficiently to routine operations, process changes, and emergencies. The balance of clarity, consistency, and task relevance is vital in building a display structure that reduces cognitive load, accelerates decision-making, and enhances plant safety and performance. Human-Machine Interface HMI Tutorial, Part 5. Effective navigation is a critical aspect of HMI design, enabling operators to access required information quickly, consistently, and with minimal cognitive effort. Navigation through the display hierarchy, whether from alarm to root cause or from overview to detailed control, should be intuitive, responsive, and structured to reflect the plant layout and control strategy. The guiding principle is that operators must reach any actionable display within a maximum of 3 interactions. This ensures quick response in alarm situations, supports fast-paced decision-making in complex environments. The display navigation system must integrate console hardware, e.g. function keys, and software configured on-screen elements, e.g. touch targets, to create a seamless interface. A consistent navigation philosophy across all consoles and display types reinforces operator confidence and reduces training effort. Figure-based navigation schemes should be developed during the design phase and reviewed with end users to ensure logical flow. Function keys. Function keys are physical or virtual one-touch buttons used to trigger frequently accessed displays, application windows, faceplates, or sequences. They are especially valuable for time-sensitive operations, such as alarm acknowledgement, overview access, or initiating guided actions, where typing or multi-step commands would be too slow or error-prone. Function keys must be grouped logically and labeled clearly. For example, keys related to alarm functions, unit overviews, or trend displays should be placed in physically adjacent positions. LED indicators on function keys, where available, provide visual cues for active alarms or system changes. For any function that initiates a plant action, such as a sequence or override, secondary confirmation should be required to prevent accidental execution. Due to their limited number, function keys should be reserved for high-frequency or high-priority functions only. Other less used displays should be accessed via soft targets within graphics. Targets. Targets are clickable or touch-sensitive areas embedded within graphic displays. They provide the same functionality as function keys but are infinitely configurable and context-specific. Targets can call up detailed displays, windows, trends, faceplates, help messages, or sequence panels. They also support navigation between display layers, such as drilling down from a unit overview to a subunit or detailed process display. For usability, target zones should be at least 2 cm² in size when using touchscreen devices. For pointer-based navigation, e.g. mouse or trackball, smaller zones may be acceptable, though consistent positioning and clear visual framing remain essential. Navigation targets should follow a standard layout across all displays, such as always placing trends, details, or control groups in the same screen region. This consistency allows operators to build muscle memory and reduces navigation time under pressure. To avoid clutter, targets should be visually integrated into process graphics using icons, borders, or highlighted areas. Their behavior must be predictable. Clicking on a pump symbol should open its detail or faceplate, not an unrelated window. Navigation hierarchy and strategy. The entire display navigation system must be structured around a clear hierarchy, typically consisting of plant overview, highest level schematic of all units with performance indicators and status, unit displays, process-specific views showing major variables and alarm states, subunit displays, equipment-focused graphics for operational control, detailed displays, fine-grained views with control logic, loops, and parameters. Support displays alarm summaries, control groups, trends, tag details. Operators should be able to move laterally and vertically through this hierarchy using a mix of function keys and targets. For instance, from a flashing alarm indicator on the overview, the operator may click a target to jump to the relevant unit display, then access the subunit, and finally open the tag faceplate, all within 3 steps. Each screen should include built-in navigation aids such as return, home, or back, targets to allow recovery from misnavigation without relying on external menus or memorized command paths. Where multiple windows are used, their layout and stacking behavior must be consistent and limited to a maximum of 4 simultaneous windows per screen to prevent information overload. Summary: navigation is more than a utility. It is a safety-critical function within the HMI. A well-designed navigation structure ensures that operators can act quickly and confidently, especially during abnormal events. By integrating function keys for priority access and graphic-embedded targets for contextual control, the HMI provides both speed and depth. Consistency in target positioning, minimal command layers, and a logical display hierarchy all contribute to a responsive, ergonomic, and error-resistant interface that enhances both operability and plant integrity.